homogeneous linear differential equation with constant coefficient. And we have seen the special type of Q of x. For that, we have seen some short methods. If Q of x is of the type e to the power ax or x to the power m or sin x or cos x or e to the power x into v, where v is a function of x, or x into v, where v is a function of x, then how to find the solution of non-homogeneous differential equation. Particularly, we want to see how to find the particular integral of these types of non-homogeneous differential equation. Now we want to go to the next chapter, non-homogeneous differential equations. And in this chapter, we want to see three more methods to find the solution of non-homogeneous linear differential equation. And these three methods are: the first method is the method of undetermined coefficients. Second method is the method of reduction of order, and the third method is the method of variation of parameters, in which these last two methods, means the method of reduction of order and the method of variation of parameter, we are able to apply these methods to find the solution of non-homogeneous linear differential equation with variable coefficient also. Up to this, in the previous chapter, we only see the methods in which we consider the non-homogeneous linear differential equation with constant coefficient. Now in this chapter, the first method is applicable for the non-homogeneous linear differential equation with constant coefficient. But the next two methods are applicable, or we are able to use this method to solve the non-homogeneous linear differential equation with variable coefficient also. Both for constant and variable coefficient, we are able to use these next two methods. Now here, first we see the method of undetermined coefficient. Now, for this purpose, we consider the non-homogeneous differential equation f of d of y is equal to q of x. Now, this method is based on the assumption that the right-hand side in this equation 1, which is q of x, is the solution of some homogeneous linear differential equation with constant coefficient. This method is based on which assumption? Try to understand. This method is based on the assumption that this Q of x is a solution of homogeneous linear differential equation with constant coefficient. If this Q of x is not the solution of the homogeneous linear differential equation with constant coefficient, then in that case we are unable to use this method, the method of undetermined coefficient. Means this method is based on the assumption that the right hand side, means q of x, is a solution of some homogeneous linear differential equation with constant coefficient. Suppose this q of x is a solution of g of dy is equal to 0, which is a homogeneous linear differential equation with constant coefficient. Therefore, therefore this q of x satisfies this differential equation. Therefore, we get g of d of q of x is equal to 0. Now, with the help of this method, means by this right hand side is the solution of the homogeneous differential equation with constant coefficient. With the help of this, we convert this non-homogeneous differential equation 1 into the homogeneous differential equation by using this g of d, which is occur in this equation. We convert this non-homogeneous differential equation into what? Homogeneous differential equation by using this operator g of d. If we apply g of d on both the sides of this equation 1, then we obtain g of d operate on f of d of y is equal to g of d into q of x. This is equal to 0 by equation 2. We know that this g of d operate on q of x, this is equal to 0. Now, therefore, we obtain this homogeneous differential equation. G of d f of d y is equal to 0. We call this equation number 3. You remember this equation? We want to use this again later on. Now, see here, suppose this m equal to, or suppose m1, m2, m3, that is mn. These are the roots of the auxiliary equations of the homogeneous equation f of d of y is equal to 0. Suppose m1, m2, that is mn, are the roots of auxiliary equations of the homogeneous equation f of dy is equal to 0. And m1 dash, m2 dash, dash 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 mk dash, these are the roots of the auxiliary equation of the homogeneous equation g of d of y is equal to 0, or g of d operate on y is equal to 0. Suppose these are the roots of the auxiliary equations of homogeneous equation f of d operate on y is equal to 0 and g of d operate on y is equal to 0. Therefore, what happens? This m1, m2, mn and m1 dash, m2 dash, mk dash, these are the roots of this homogeneous differential equation 3. All these are the roots of homogeneous differential equation 3. Now, the general solution of given non-homogeneous linear differential equation 1 is y is equal to yc plus yp, where yc is obtained from the known values of m1, m2, mn. Now we have seen that this m1, m2, mn, these are the roots of the auxiliary equations of the homogeneous differential equation f of d operate on y is equal to 0. Therefore, from this we are able to find yc. Yc is obtained from these values of m1, m2, mn. Now, the general solution of this equation 3, I have told that, remember the equation 3, which is g of d, f of d operate on y is equal to 0. And the general solution of this equation 3 contains this yc, complementary function of this equation 6, or complementary function of the given non-homogeneous differential equation. And therefore, it is of the type y is equal to yc plus yp dash. This is of the type yc plus yp dash. Now here, but any particular solution of given non-homogeneous linear differential equation 1 satisfies this equation 3, means g of d, f of d of y is equal to 0. Therefore, we obtain from this that this yc plus yp dash, this must satisfy the given differential equation 1, means f of d of yc plus yp dash is equal to q of x. We simplify this left hand side. We obtain f of d of yc plus f of d of yp dash is equal to q of x. Now we know that f of d of yc is equal to 0 since it is the solution of f of d of y is equal to 0. Therefore, we get f of d operate on yc is equal to 0. And then finally, we get f of d operate on yp dash is equal to q of x. We want to use this equation when we want to solve the example. Means what we can conclude from this yp dash satisfy the given differential equation 1. This yp dash satisfy the given differential equation 1. So after deleting the terms of yc from the general solution of equation 3, use the function yp dash such that with proper choice of the constants in yp dash, the equation 1 will be satisfied. We choose the proper by proper choice of the constant in yp dash, it satisfies this equation 1. And after determining these coefficients properly, means arbitrary constants in yp dash, after determining this, we write this yp dash is equal to yp, means we substitute the value of these arbitrary constants from which we obtain from this equation. We substitute from this equation, we obtain the arbitrary constants in yp dash, and then we substitute this value of arbitrary constants in yp dash. We call it as to be yp, which is a particular solution of the given non-homogeneous differential equation. And then we write the general solution of the given non-homogeneous differential equation as to be y is equal to yc plus yp. And if we solve the given non-homogeneous differential equation by this method, then it is called as the method of undetermined coefficient, or the solution of given non-homogeneous linear differential equation by the method of undetermined coefficient. I hope you understand this method properly. I will repeat some important points in this method. This method is based on the assumption that the q of x must be a solution of some homogeneous linear differential equation with constant coefficient. This method is based on what? By the assumption that the q of x must be a solution of some homogeneous linear differential equation with constant coefficient. And by using this, suppose this right hand side q of x is the solution of g of d y is equal to 0. Then by using this operator g of d on the given equation 1, we convert this non-homogeneous linear differential equation into the homogeneous differential equation. And then we apply this method. I have explained detail how to, what is this? The method of undetermined coefficient. We see one example based on this topic in today's lecture. Solve the equation d square plus 3d plus 2 of y is equal to 12x square by using the method of undetermined coefficient. Now, the same example we are able to we are able to solve by the method which we have seen in the previous topic or in the previous chapter, in which q of x is of the type x to the power m. By that method also we are able to find the general solution of this differential equation. But here we want to find the general solution of this differential equation by using the method of undetermined coefficients. Now here for this purpose, as usual, first we find the complementary function. For this purpose, consider the associated homogeneous differential equation d square plus 3d plus 2 operate on y is equal to 0. From this, the auxiliary equation is m square plus 3m plus 2 is equal to 0. We factorize it, m plus 1, m plus 2 is equal to 0. Therefore, m is equal to minus 1 minus 2 means auxiliary equation have the real and distinct roots. Therefore, the complementary function yc is equal to c1 e to the power minus x plus c2 e to the power minus 2x. First part is easy. We want to find first yc, complementary function of this non-homogeneous differential equation. Now to find the particular integral by the method of undetermined coefficient, for that purpose we must know a homogeneous linear differential equation with constant coefficient whose solution is 12x square. Means we want to find that homogeneous linear differential equation with constant coefficient. Now see the technique how to find this homogeneous linear differential equation with constant coefficient whose solution is 12x square. Now see here, if we see this q of x, here it contains the term of x. We have seen in the previous chapter, according to the roots of auxiliary equation, we write the general solution. Now here we go the reverse way. According to the solution, we want to decide what are the roots of the auxiliary equation. And from that we write the differential equation, homogeneous differential equation with constant coefficient. Now here, if the terms of x occur in the solution, this indicates that the roots is repeated. Now here, if there is a term of sine or cos, then this indicates that the roots are complex. If the terms of sine or cos comes, then this indicates that the roots are complex. And if the terms is of the type e to the power ax, then this indicates that the roots are real. I say you the things. Now see here, if in this q of x is the term is of the type e to the power ax, this indicates that the root is real. If it contains the term of sine ax or cos ax of this type, then it indicates that the roots are complex. And if the terms contains, means q of x contains the term of x or powers of x square, x cube and so on, this indicates that the roots are repeated. Now here, if we see this, the right hand side, q of x contains x square. And when this term x square comes in the solution, we have seen in the previous chapter, the x square comes in the solution if the roots repeated thrice. If the roots repeated thrice. Now, since x square is there, therefore, the roots repeated thrice in the auxiliary equation. This is our first conclusion. Now the second, it does not contain the term of sin ax or cos ax, therefore roots are real. Means roots are real and repeated thrice. Now which real root repeated thrice? Depend on the term of e to the power ax. Here there is no term of e to the power ax, means we write this term as to be e to the power 0 into x, and e to the power 0 into x is 1. Means this indicates that a is 0. Means auxiliary equation have the roots 0 and it repeated thrice. Or you may use the notation e to the power mx. As you use the notation, auxiliary equation means here m is 0 and it repeated thrice. Means since 0, 0, 0, these are the roots of the auxiliary equations. Therefore, what is the factor of auxiliary equation? M minus 0, m minus 0, m minus 0 equal to 0. Means m cube is equal to 0. Therefore, what is the homogeneous linear differential equation with constant coefficient whose solution is 12x square is the d cube y is equal to 0. Are you understand this technique? How to find the homogeneous linear differential equation with constant coefficient whose solution is 12x square. I explain this technique. I hope you understand this technique properly. Now, therefore, here g of d is equal to d cube from this. And then we apply this g of d, means d cube on both the sides of this equation 1. Then this equation 1 becomes d cube into d plus 1 into d plus 2 of y is equal to d cube of 12x square. And d cube of 12x square is 0. I have written this directly. D cube of 12x square is to be 0. We obtain this equation. Now, therefore, what is the general solution of this homogeneous differential equation 6? Roots are minus 1, minus 2, and 0, 0, 0. Therefore, the general solution of this equation is C1 e to the power minus x plus C2 e to the power minus 2x plus C3 plus C4x plus C5 x square from this equation 4. Now, if we see from this equation 4, this first part is yc, right? Therefore, this second part we call it as to be yp dash according to our theory. But for our simplicity to solve the example, we consider this yp. But yp does not contain the arbitrary constant. Particular integral does not contain the arbitrary constant. Therefore, here we want to find these values of C3, C4, C5 or numerical values of this, and for that purpose this yp satisfies this differential equation 1. Using this concept, we are able to find the proper values of this C3, C4 and C5. Therefore, we get d square. From this yp, find yp dash, yp double dash, and then we substitute this in equation 1. Yp dash, yp double dash, yp satisfies equation 1. Therefore, we get d square plus 3d plus 2 operate on yp is equal to 12x square. If we simplify this bracket, this is d square of yp is yp double dash, and yp double dash is 2c5 plus 3 derivative of yp means yp dash is c4 plus 2c5x plus 2 times yp, yp is c3 plus c4x plus c5x square, and this is equal to 12x square. We substitute these values to be here and we get this is equal to 12x square, collecting the like terms and so on. Here we by equating the coefficient of the like terms, we get 2C5 plus 3C4 plus 2C3 is equal to 0. C5 plus 2C4 is equal to 0 and 2C5 is equal to 0 means the coefficient of constant term here constant is 0. The coefficient of x, there is no term of x, it is 0 and the coefficient of x square in this way. Now from this equation we obtain C5 is equal to 6. We substitute this value to be here, it becomes 36. Right hand side it becomes minus 36, then divided by 2. We obtain C4 is equal to minus 18. Substituting the values of C4 and C5 in this equation, we obtain the value of C3 as to be 21. And then we substitute these values of C3, C4 and C5 in YP, we obtain the particular integral of the given non-homogeneous differential equation. Means we obtain YP is equal to 21 minus 18x plus 6x square. And then we write the general solution of given non-homogeneous differential equation is y is equal to yc plus yp is equal to C1 e to the power minus x plus C2 e to the power minus 2x plus 21 minus 18x plus 6x square. And this is the general solution of given non-homogeneous differential equation by the method of undetermined coefficient. We see more examples on this topic in the next lecture. I hope you understand this. Now we stop our today's lecture.